So this is EE 619, lecture 20. And we are now looking at dynamic circuits. So the general topology is as shown here. You have the pull-up network as a single PMOS connected to clock signal. The pull-down network also has the logic, which is a function of multiple inputs. And we added one more NMOS transistor connected to the clock so that whenever the pull-up network is on, we are guaranteed that the complete pull-down network is off. So let me sketch out the clock waveform. Now we said that whenever the clock is equal to 0, your PMOS is on, which means the output is pre-charged to VDD, up to logic 1. So during the 0 phases of the clock, we are in pre-charge phase. And whenever the clock is 1, then your pull-up network is off. This network will now evaluate the logic that is being implemented within this PDM. And based on it, this will either let the output capacitor float or it will conditionally discharge the output. Okay, so we did this analysis assuming that the output capacitance did not have any leakage. What happens if there is a leakage in the output capacitor? Okay. So during this stage, because there is nothing to reinforce it back to VDD, this can start to leak. Now, if the leakage is severe, it might cross over the midpoint voltage of the next logic gate. So now this is a serious problem, right? Because your functionality, the output itself can change. What is the solution? So we have to keep restoring the logic, which means, I mean, I might have as well connected this to ground. Right? Use a larger frequency. But let's listen to this answer. For the whatever we did for the mux. So you could do that, but then you will increase the load at this node again, right? So the other solution is the time period which is available for this capacitor to completely discharge without being reinforced through any other mechanism is basically half the clock period, right? So the other solution is to make sure that T clock by 2 is small, or effectively the clock is small, which means your frequency has to be slightly large, right? That is also true. Yeah. So not really. So what is your suggestion? Something like this. So this solution might be okay in certain cases. Where it will not be okay is because you have a very long pre-charge phase. The evaluate phase is now very short, which means you are holding the output for the next stage for a very short period. So that might make it difficult to meet the timing constraints overall. Now, you can, of course, check it and see if this is a problem. If not, you can use it. Okay. So for both circuits, we expect to see a constraint in terms of the maximum frequency. The circuit is going to operate till a particular frequency. Now, your dynamic circuits has a constraint on the minimum frequency as well as on the maximum frequency. So there is a minimum frequency constraint. This also means that your dynamic circuit is now more sensitive to noise. Now, during the stage when it is floating, if some noise had coupled to this node and it sort of reduced the voltage at this node, there is nothing to bring it back to the regular levels. So you also have to take care that this is properly isolated from unnecessary coupling capacitances that could, wiggle this value a lot. Okay. So compared to a regular static CMOS circuit design, this is less robust and is more sensitive to noise. So I had asked you to implement inverter NAND2 and NOR2 and to size them. So let us do that together. So our inverter circuit is like this. Let's say A is my input, this is phi, and this is Y. Any comments on how I should size my PMOS? Again, our aim is we usually compare it with the reference CMOS inverter, which for us right now is 1 and 2. So how should the pull down network be? This has to be 2 and 2. What about the PMOS? Okay. So now here is a question. For the PMOS to actually pull up the node Y to VDD, you have half a clock period, right? So why not go with the minimum size? Are we really worried about how long it takes for the pull-up network to act? Why should it be? R into C should be lesser than? So as long as the time taken for this MOSFET to charge the node Y to VDD is lesser than half the clock period, we are okay, right? And in most cases, that will be the situation, right? So because of this, we really don't worry about the sizing of the PMOS. We are more interested in how fast the pull-down network can act. And if the pull-down network has to be made faster, then we need to reduce the capacitance at this node, which means it is better to have the size at 1. Okay. So now based on this, can you calculate what is the logical efforts? What comment can you make about GU? Is this calculation relevant, first of all? So in the evaluation phase, there is no rising edge, right? You are either going to hold it as it is, or you will have a falling edge. So the calculation of GU is not even relevant. Is that clear? Okay, so we are discussing about logical effort with respect to A, right? How the delay from A to Y is changing. Now, in this particular case, during the pre-charge period, you take half a clock cycle to pull this up to VDD, right? We are not worried about the output during this duration. Now, once this is done, your output is either going to remain in a floating state, that is, it remains at VDD, or it can have a falling edge. Okay. So there is no rising edge that you will see during the evaluate phase. You don't see a rising edge during the evaluate phase because the pull-up network is off during the evaluate phase. So what is the significance of calculating GU here now? Not needed, right? You only need to worry about the falling edge transition. During the pre-charge phase, as long as you have ensured that it will reach to VDD, so maybe it is charging very slow, but as long as it is reaching VDD before the pre-charge phase ends, we are fine. And the pre-charge phase anyways is T clock by 2 long. So you will need to simply ensure this condition. Once this condition is ensured, you are fine. Okay. Now calculate GD for me. So this is irrelevant. So GD is basically the input capacitance associated with A, CA, divided by the total input capacitance of the reference CMOS inverter. How much do you get? This is 2 by 3. So here you have 2C. From here you have 3C. So you'll get 2 by 3, which is now smaller than the reference CMOS inverter's logical effect. And here so when we were using a pseudo NMOS based logic, you also had to worry your logical effort associated with the pull-up network was getting worse, right? Here, if you are comparing the delays in the evaluation phase, the delay in getting to VDD is basically 0 because you're simply holding the value there as it is. So repeat the same exercise for NAND 2. You are making the A minimum sized and phi as. So if you make this also as 1, then the effective resistance is higher than the. So here you have a pull down resistance of R. Here the pull down resistance is 2R. The output drive current is now much lesser compared to a reference CMOS inverter. The ratio 2:1 we keep in a reference CMOS inverter so that the pull up and pull down network has the same RC, right? In this particular case, the pull up network has half a clock period to charge. So our priority now is to focus on the pull down network. Is that clear? We don't have to, right? We generally care about the relative strength because we want to make sure the rise time and fall times are roughly in the same range. Here we care about only the pull down strength. Why not reduce the size of phi even further? You can keep it to the minimum size. For now, I have assumed that size 1 is the minimum size possible. So can you implement NAND 2? How would you decrease the size of the? Increase the size of the pull down network. So you increase the size of the pull down network, your capacitance here will increase, right? So if the load capacitor being added is not very large, then you might not see much benefit. But if the load capacitor is large, then this is the sizing algorithm that we regularly use, right? You can upsize the pull down network so that you have larger drive strength and smaller delay. So do this for NAND 2 as well as NOR 2, both dynamic implementations. It is 1 for the NAND gate. So the gate will be like this. So the input capacitance associated with one of these inputs is 3C. So it is 3C divided by the input capacitor of the inverter, which is also 3C. So you'll get 1. Now for the NOR 2 circuit, again, we are not worried about the pull-up strength, assuming that it is able to pull up the voltage in half a clock period. So we put it at minimum size. And these have to be sized at 2. So your GD is now 2C divided by 3C, which is set 2 by 3. Any questions on this? Okay, good. So now let me give you one more waveform to solve. Which one? The DC VSL? That you should be able to do the same thing. I have to check whether the PMOS sizing needs to be considered. PMOS is always on, so it should be similar. The reason why we went to pseudo NMOS is because we were not worried about the pull-up strength. So you can apply the same sizing principle there also. Yeah. So it is continuation from the pseudo NMOS logic, right? So however you have sized the pseudo NMOS logic, the same thing will get repeated. So for the pull-up network, there was a WP by WN constraint because of the VOL. Right? Now that constraint is no longer true, which means you should be able to keep the PMOS at minimum size. So this is a regular inverter circuit again. Let's say your clock waveform is as shown here. The A is changing like this. Can you sketch the output? So the pre-charge phase is when phi is equal to 0. Evaluate phase is when phi is equal to 1. So during the pre-charge phase, you don't have to think about anything. The output is VDD. Now for the evaluate phase, the output is conditionally discharged. So you need to look at what the value of A is. Here A is equal to 0. So the pull down path is off. So it will hold the value. Here you have a rising edge, which means the NMOS has now turned on and it will pull the value down to 0. So here, because A is on, it will come down. Then what happens? So till this point, you have the NMOS on. After that, the NMOS turns off, right? But the pull-up network is still not on. So the same value will remain here till the next pre-charge phase. So now this is a problem, right? We expect to see the correct value during the evaluate phase, and you have an incorrect result in this region. Why did this happen? Correct. So basically, in the evaluate phase, your circuit can correctly respond only to rising edges, right? Which means now if you're using a circuit like this, you have to ensure that either all the transitions in the input happen during the pre-charge phase, or if any transition is happening during the evaluate phase, it has to be a rising edge. Okay, and this is something that you guys can ensure, right? You make sure that the input is either changing during the first half of the clock cycle when it is in pre-charge, or only rising edges can happen during the evaluate phase. So this is something that you'll have to keep in mind. Now let us consider a situation where we begin to cascade these dynamic circuits, right? So construct a circuit, construct an AND circuit, which is a cascade of NAND and a NOT. You can of course assume that the inputs will have only rising edges at the beginning of the during the evaluation phase. So you have an AND. We can assume that B remains at 1 throughout and A is going from 0 to 1. So no issues here, right? The one input is stable. The other input is going from 0 to 1. That also during the pre-charge phase. So can you plot Y1 and Y2 and tell me if you see any issues? So Y1, during the pre-charge phase, both Y1 and Y2 are at VDD, right? Then once you have the rising edge in the clock, because A is now 1 and B is now 1, this will start to discharge, right? And then it comes down to 0, and then here again it will pre-charge. What about Y2? At the instant when the clock has gone high, the input to its NMOS transistor is closer to VDD. So this is now going to start to discharge, right? Halfway through this discharge process, the NMOS will turn off because the input Y1 is now below its threshold voltage, right? So at this instant, this is now going to turn off, and then it will hold whatever value was there at that point at which it has turned off. What should have been the correct value of Y2? It should have been VDD, right? Now, depending on the rate at which Y1 was falling off, this could either be an intermediate voltage or it can even come down to logic 0, right? So now we have a problem again. So we said that individually the gate will work fine as long as you ensure that the input is always a rising edge during an evaluation phase. But the moment we put two gates together, we see that the second gate output is failing, even when we ensure that the first gate has the right sort of input. What do we do now? So why do you suggest that? So the solution that he is suggesting is, right now our cascading is happening like this. You have a phi, then PDN and a phi, and we are taking the output from here, and we were feeding it as input to the next gate, which also had a PDN. Right? So if you ensure that the inputs here are always rising edges, you will definitely have a falling edge here. You cannot have a rising edge here during the evaluation phase. Now, if you have a falling edge here, that is a problem for the second gate. So we make sure that a falling edge is not a problem for the second gate. And you can do this by pushing the logic onto PMOS side instead of the NMOS side. So you will have a pull-up network here. And then you can take the output from here. So now if you have a falling edge here, that will turn on this pull-up network. So if you ensure that you will only have rising edges here during the evaluation, that guarantees that you will only have a falling edge here during the evaluation phase. And the pull-up network will turn on in case there is a falling edge. Right? So let me quickly elaborate on this a little bit more. Let's sketch the NAND gate that we are working on, right? So this is 5. We'll have A and B here. This is 5. So this is our first output Y1. Now this goes as input to a PMOS transistor. And this is now your Y2. Now let's say when phi is equal to 0, we want it to be in pre-charge phase. We want both the gates to be in pre-charge phase. And when phi is equal to 1, we want both of them to evaluate. So what signal should I connect here to the input of the NMOS? This has to be phi bar. Right? So this also should be phi bar. Okay. So now for the same scenario that we drew earlier, can you sketch Y1 and Y2 for this case? During the pre-charge phase, what is the value of Y1 and Y2? Y1 is at 1, Y2 is at Y2 is at 0. Right? So now at this instant, because the pull down network is completely on, this will begin to fall. So if this is beginning to fall, initially it will hold the value at 0. And once it crosses the trip point, this will now begin to rise. Right? So this way you can have the correct results. Etc. And this sort of arrangement is called as NP-CMOS dynamic circuit. Because you have the logic implemented on N side in one gate, and then the immediate gate will have the logic implemented on the P side, on the PMOS side. Is there any other solution? Is there anything wrong with this particular solution? Any reason why we do not want to consider this? Yeah. This requires both clock and clock bar. So in case you don't have clock bar, then you may want to consider other methods. You can create clock bar, right? So it depends on whether you want to invest in generating clock bar and then driving it with the buffers. Usually not an issue, right? But is there any other way in which you can solve this? It's always nice to have more than one method, right? Provide Y1 as 5. So how do you ensure about the recharge phase and evaluation phase correctly then? So the whole problem is happening because you have a falling edge appearing at the input of the NMOS, right? In what other way can I avoid this falling edge? Add an inverter in between. A falling edge happening during the evaluation phase is the problem. So even if you say, you're saying that the Y1 can go down to 0 very fast. So even if it is going very fast, your Y2 voltage is likely to dip a little and then stay at a value lesser than VDD. We don't want to risk it, okay? Because this is a functionally incorrect circuit, then you will get incorrect outputs. So falling edge is a problem because as we saw here, when you have a falling edge in A, we expected our output. So this is an inverter. If A is 0, we expect the output to be 1. And in the evaluation phase, we expect that the circuit is going to give us correct results. It should be high, right? But when you have a falling edge here, because the signal was 1 prior to this, your capacitor has already discharged. It's at 0 now. Now, if you have a falling edge, the pull down network turns off, but you don't have a pull up network to pull this back up to VDD. So you can have an incorrect result in the evaluation phase. Yeah, you ask some other question. Oh. So the problem is happening because we have a falling edge in this part. So another solution is to simply add an inverter in between so that the inverter input is a falling edge, inverter output is a rising edge. Not if you add another inverter at the output of Y2. We will discuss that in a minute. So the circuit being suggested now is to have Y1, Y2, Y3, Y4. Yes. So to answer that question, so the question being asked is, this is anyways a NAND circuit that we were trying to implement. So if you have AND and an inverter here, it's already NAND. That is a very valid argument. I use this as a sample circuit. In actual cases, you have to imagine that the pull-up network of the second, pull-down network of the second gate is something complex, right? So this is a very simplistic explanation being given. But the same logic you can apply even when the network here is something very, very complicated. This can increase the delay. It now depends on what the delay here was originally, right? So sometimes adding a stage is also helpful in reducing the delay, right? If the signal was already rising like this, adding an inverter here will make sure it is rising much sharply. Sorry, it is, yeah. So the signal here can now rise much sharply, assuming the input capacitance of the first inverter is much smaller. And it is driving the next node, which means that can also fall very sharply. So that way, this may be useful in certain cases. Depends on the application. Okay. So now I will leave this as a homework for you to plot the waveforms. So you will have to sketch for a given phi and an A. You have to sketch Y1, Y2, Y3, Y4, etc. But what you will see is corresponding to a transition in Y1, you'll have a falling transition here, a rising transition here, and a falling transition here. So one event is triggering the transition in other events. It's sort of like a domino. Therefore, this is called as a domino circuit. So please sketch this as a homework. Right. So now the other question is, what sort of inverter should I use here? Any suggestions? CMOS inverter. Okay. In that CMOS inverter, is there any other information that we have which we can use to optimize it? During the evaluation phase, what do you expect to happen at the output of the inverter? During the evaluation phase, it can either remain at 0 or it can only fall, right? So does it remain at 0? It's not correct, right? During the pre-charge phase, this will be at 0. This is at 1. Now, during the evaluation phase, this can go either remain at 1 or go from 1 to 0. This can only fall, and this can either remain at 0 or go from 0 to 1. So this inverter, during the crucial evaluation phase, is going to see only rising edges. Now, how should you design your inverter? What is this type of inverter called as? Where you take an inverter, you optimize it only for one of the transitions. Refer to your notes. Yeah, it's a skewed inverter. And now we are skewing it in favor of the rising edges. So what is that inverter called as? High skew inverter. So a good recommendation for this inverter would be to implement it as a high skew inverter. Is this clear? Zero to. You are decreasing the GU. So now let's summarize all the results we have on dynamic circuits. What are the pros? So that is no need to keep the logic always. So output is not available at all times. So that is a con, right? So output available only for half a clock period. What else? Does it have static power? It doesn't have static power, right? What about the logical effort? So its logical effort is smaller. What comment can you make about the parasitic delay compared to CMOS transistor? CMOS, complementary static CMOS logic. Why is it smaller? Correct. So the logical effort is smaller. The parasitic delay is also smaller. Number of transistors. So for n inputs, how many transistors do you need to use? You need only n plus 2. And this is compared to 2n transistors in complementary static CMOS implementation. So the number of transistors is also small. What are the disadvantages? So one, we already said that output is available only during T clock by 2, right? What is a major disadvantage? So there is a F min constraint also. There is a minimum frequency with which this can operate. But a bigger problem is, so there is a constraint on the type of transitions you can have during the evaluate phase. Now it could be rising or falling depending on whether the logic is on PDN or PUN side. But the major drawback is, you can, no? So you will either have to use a domino circuit methodology or a NP-CMOS methodology. Then you can cascade any number of gates. You need a clock signal, which means now the clock buffer, you will have a clock buffering tree to route the clock to different parts of the circuit. So you'll have to spend some power and area in the clock buffering. And this gate is now non-restoring. So when your node is floating, if some glitch occurs there because of coupling from another transition, that can affect your output. Right? So that is a major drawback compared to CMOS-based static complementary CMOS-based implementation, because there you always have a direct path from VDD to the output or from ground to the output. So even if there is a minor glitch, it will auto-correct itself. It will correct itself within the next few seconds. That is not possible with a dynamic circuit. If once your output glitches to a value which is not under the control of, let's say, the output goes below VDD and your pull-up network was off, it cannot come back to VDD. So this gate is now non-restoring in nature. So now I have a very interesting question to ask you. So far, we have been working with this architecture, right? You have the phi here. Let's assume that the logic is being implemented on the pull-down network side. And you have another phi here. And this is your output. Now, another possible option was to interchange the position of this PDN and this transistor, right? I could have connected it in this manner. So let me, so this is phi. This is again the output. Let's say this is case 1 and this is case 2. Let's call the total capacitance at the output here as C1 and the capacitance here as C2. What comment can you make about the relative values of C1 and C2? Which is bigger? C1 is bigger than C2, right? Given that C1 is bigger than C2, shouldn't we opt for this topology? That should ideally give us slower parasitic delay, right? Everybody agrees? Yeah, but we don't, right? Because this circuit has a problem. So please think about why we would prefer case 1 circuit over case 2. So you can think about this and we can discuss this in the next class. Is the question clear? So this is the second homework for you. So now dynamic circuits are used in situations when you really want to improve the clock speeds, right? So this is used in GPUs, graphical processors and all, where higher clock speeds are required. So you will have to be careful whenever you use it, because there is a minimum frequency constraint, as well as constraints on, because it's non-restoring in nature, it has to be properly isolated from glitches. But with the help of dynamic circuits, they have been able to increase the speed of processors a lot. Okay. Now let me give you another scenario. Let's assume that you are implementing multiple blocks of combinational logic. Let's say you have C1, C2, and C3. Let's say both C1 and C2 are very fast, and C3 is very slow. So whenever an input here changes, the input is going to, your output from C1 is going to come very immediately. This is also going to come immediately. But C3's output is going to take a long time to appear at the output. Now, in this case, there is a problem of how to arrange the inputs, right? Because let's say C3 was processing the previous input and it required this value to be stable here. But because C1 and C2 are very fast, it might appear and correct the data here very quickly, right? What is a possible solution now? So you need something here that can hold the previous value for you, right? You need an element that will help you sequence the events that are occurring. So for that, we use a flip-flop or a latch. So let me right now introduce flip-flops here. right? And we can operate all of them at a particular clock frequency. Now this clock is going to determine the rate at which your output, final output is going to appear here. The problem was that without these sampling elements in between, when your input changes, the corresponding output is going to propagate till this point very quickly, right? But then C3 is going to take its own sweet time for it to reflect that output, reflect that corresponding output here, correct? Which means by the time C3 is evaluating the output correctly for a given input, the data would have already changed. So we need some sort of mechanism to hold the data in between. Okay? For that, we can introduce some sort of memory element which gets triggered at certain edges. And for that, we use a clock signal. So you could potentially use one flop here between C2 and C3. That is correct. But let me show you how the overall system works, right? Now, if you have a data input here, as long as you take care of the relationship between data and clock, right? And you know that the combinational delay is much lesser than a clock period, then you are guaranteed that every rising edge of the clock, you will see an output. So even if you use a flop here, a flop only at this position, you will still have to take care of the time at which the data and clock are entering the system. Because now it is a relative position of data and clock that matters, right? Every time the data has to be ready before the clock edge. And this component will ensure that it processes, the data will be ready much before the next clock edge, right? But it will simply hold the value because its input is not changing. Now, this one will process it very quickly. Again, the data to the next flop will be ready much before the clock edge. But the output here doesn't change because the input is constant. This component will get some input to the system, right? It is going to take a long time for it to process. But if you control the clock period appropriately, you are ensuring that the data here remains constant for as long as it is needed for C3 to process it. This is okay. So this is one of the motivations behind requiring sequential logic or memory elements in the circuit. So let me show you another example. And so this particular case is called as a pipeline system. Correct. So we are assuming that the data is ready within one clock period. So even C3's delay has to be smaller than the clock period that you are choosing. So you will have to choose the clock period based on your circuit. So another possible scenario is, let's say you have this combinational logic. It has multiple inputs, let's say I1 to IN. And it has corresponding outputs, let's say O1 to OM, right? Now, this is something that you will see when you implement this project. The output of this combinational logic also depends on a state variable. For example, if an IC is in power down mode or if it's in sleep mode versus it is in active mode, right? The outputs are going to be very different compared to these inputs. And this information about what mode the IC is in will be stored in a state variable. Right? So you would have to give the current state variable. And based on the current state and the inputs, it will generate the outputs as well as the next state. And this next state information has to be stored within the system. Right? So you will have another flop here. This is the data. This is its output. And that again feeds back in like this. And this is what we call as a feedback system. So whether you are implementing a feedback system or a pipeline system or a combination of both, you need some sort of memory elements in your circuit. And with this, we come to the next topic, which is on sequential logic. So in the next class, we will start by looking at the top level properties of flip-flops and latches. And then we will slowly go into the transistor level implementation of these circuits. Thank you.